Glad to be here. Oh, Wolfgang, it's been many years.
Yes. Good on IT distance.
Yeah. Okay, we're a few minutes past, 4 p.m. in Europe and 7 a.m. in Pacific time in the US. So let's get started on the second day. We're approaching 60 participants. So it's my great pleasure to welcome you again to the second day of the second ACM IEEE workshop on machine learning for CAD. And today we will start with the keynote by Wolfgang Ecker on SoC design automation with machine learning. It's time for research. Wolfgang is working with Infineon. He is a distinguished engineer there and also adjunct professor at my university, Technical University of Munich. He has co-authored hundreds of papers, received many best paper awards, and also some years back he received the German EDA Achievement Award. He's a member of the German National Academy of Science and Engineering. Within Infineon, he leads the deep learning internal think tank. And also he advises the German federal government on artificial intelligence. Thank you very much for accepting our invitation, Wolfgang. And now the floor is yours.
Thanks all for the nice invitation. Just as a hint, this talk has been enabled by many of my colleagues, which are working on machine learning for AI and also in hardware. Many thanks already there, and also thanks again to the organizers to organize such a nice conference in this under these hard circumstances. No, it does not move. Why does it not move? Now it moves. A bit slow. Okay. What I'm going to cover, I will start a bit as warm-up to say some words about general AI, narrow AI, old AI, and machine learning. I will address a point which I headline business behind machine learning in EDA, address another challenge, which is training data collection. I already will show some use cases there from our industrial practice. Afterwards, I will show some more industrial use cases. And last but not least, I will motivate that we need more research, machine learning EDA. We see the possibilities, but we are far away from being there. So what's AI? How you can distinguish AI? So the more organizations you work with, the more definitions of AI you get. What I like most is what we call AI, something that is a capability of some information technology system. And this system provides features which so far they have been reserved for human beings and human intelligence. This is also nice because it's the definition is continuously evolving. That means it also says that we expect even more and more advances in AI and forthcoming and possibilities to improve our daily life. What's inherent in this definition is also that artificial intelligence is a technology, and we strive for new technologies to improve our life. In AI, we speak about the narrow AI or weak AI. That is something that partly outperforms humans' intelligence. Also here you can make a general picture of technology. Since thousands of years, human beings invented things, we call it technology, that helps them or that makes them stronger here and there. And now there's a discussion about general AI or strong AI that is said to outperform humans in all tasks to be performed. the discussion was a bit stronger a year or 2 years ago. At the moment, I think we are more in a realistic curve on what AI can do and what AI cannot do. Nevertheless, let's start with a nice drawing. So assume over the years the machine intelligence increases, and it takes more and more off. And what I said, strong AI is set to catch up with human beings. By having so many computers, another case may happen, namely that the intelligence of our human being continuously decreases. Then you want to say this is not possible. We have more and more inventions, greater and greater technologies. And we observe this that for decades, the IQ of the average IQ of humankind is decreasing and decreasing. So maybe that AI will not catch up, but maybe human being will, so to say, decrease their intelligence step by step. I personally don't take this serious, but maybe take this as something to think further. Artificial intelligence, as you know, is not one technology. It's a composition of many technologies evolved over many years, and also incorporating solutions from other technologies. I recently learned about an FFT net. In my time at university, this was called system theory, but anyhow, now it's going to be part of AI as well. As I said, AI is quite old, and for example, the technologies behind deduction, reasoning, problem solving, knowledge representation, and so on, have a highlight about 30 years ago. And what we know about that is, for example, symbolic math, Boolean reasoning, knowledge representation, expert systems, rule-based systems, evolutionary algorithms, genetic algorithms, and there are definitely more. Interestingly, silently, many of these techniques made it in EDA tools. So formal tools like equivalence checker or property checker is not possible about symbolic math. Same holds for ATPG tools. STA works with reasoning, the false path problem, and STA utilizes temporal logic. In synthesis, we have Boolean optimization. And interestingly, in EDA, we do learning quite a while, but we don't call it learning, we call it model fitting. So we build a lot of models for our transistors, for example, and then we fit the parameters of these transistor models that the execution or simulation of a model fits best with the things that we measure in reality. If I said, okay, we know model fitting quite a while, there's a big difference. To build such a model, quite a substantial R&D effort has to be spent to define the structure, the math behind the model, and compared to our today's machine learning, the number of parameters is drastically smaller. So the learning problem is much simpler. What's important for me, what I want to say is that if we consider AI for a while, then silently a lot of things which are associated or have been associated with AI already made it to EDA. Now let's focus a bit more on when the new AI, everything which is behind machine learning, everything which is out, this is part of this AI hype curve, which I think started about 8 to 10 years ago. And before going to more technology, let's already start to think about some business behind machine learning in EDA, because if we want to make it a success, sooner or later, we also have to think about the business. And there it's a bit, how to say, disappointing. Remember, there have been times where conferences took place in really, we had face-to-face meetings. At DEC 2018, there was almost no session with not at least one AI paper, many tutorials, embedded talks, discussions about AI were there. If you now take a look at what we have commercially available, I would say it's not that much. So the promises made were quite high. What we see is might be more, and we are striving to see more and get more. Unfortunately, it does not seem to be so easy to get the machine learning in EDA tools. One thing, as I said, is a business model, and what I like to put here as an example is the famous Google. And Google is the AI company and started with search engines and with AI technology. The business model was advertisement. Yeah, they don't sell the search engine much. It was possible in the early days, but the money comes from advertisement. And I like this example because you see here that the business model and the underlying technology may be totally different to make it. And this is something what also is a challenge for AI and EDA. Let's say if EDA makes an incremental enhancement, so where the tool is a bit better, then as a customer, and then I and my company is a customer, we simply expect some incremental improvement over time as standard evolution of a tool. Yeah, if I increase the efficiency too much, let's say I find a way to reduce the simulation effort by 3/4, just to take any number, then also means that we have to license 3/4 less tools for a time, which is at the moment a loss of license fees at the EDA side, or on the other side, an AI-based tool which reduces the license that much must cost at least as the saving or the reduction in EDA licenses. Maybe this also shows that efficiency improvement is more than licenses. Is for us, a designer, it's more to get faster results from the tools, to make a faster progress. Maybe this is also to think about new ways of business models at all. Yeah, and then what we also have not seen so far, that we are really totally new tools, which is also often a chance for new business. So far, I'm not aware that I've seen any EDA tool which is with AI, which makes things totally different, that means different as we are used to today. And yeah, I think the Google way of making the business with advertisement might not work here. The EDA has another challenge to overcome, at least when interacting with the worldwide AI community, and the point is the closed EDA system. To illustrate this, I just want to summarize an example which we did at Infineon. So we had an own solution to randomly and partially manually generate test cases. When we simulate it, we have the coverage results, and after long randomization and manual work, we get the expected coverage. In order to speed up the process, we took the simulation runs and trained an AI-based randomizer. When we used inference-based randomization instead of constrained random generation, and finally we made it up to 60% effort reduction in getting the coverage closer. And effort reduction is really the manual effort meant here, not the tool runtime. Of course, it was a success, and clearly we want to generalize it because it was for a very specific use case. And unfortunately, we failed. Simply, we didn't have access to the commercial UVM tools to hook this inference-based randomizer to the UVM tools. Another point in machine learning in EDA is the training data collection, and I even should say the lack of clean data. And that's really sounds a bit crazy because we learn every day machine learning is so successful because the number of data available and the things running around the world is exponentially growing. And now I'm claiming that we like data collection. Number one, we need so much of data to train things that we cannot make this data collection by inspecting hardware. Whereas I want to say that we also use machine learning in our fabs to optimize our processes, but I'm sure that many, if not all, semiconductor companies do the same. What's a way to get your EDA tool trained? So you need your design database, what you need in the middle. Number one, you need a single database because you want to correlate data, or at least a database that looks like a single database to do correlation. Now with this database, when you can train AI algorithm, and we get something what's mentioned here, trained AI EDA tool. To fill the database, you need a lot of designs, and to get the designs, or at least the virtual designs or the design models, you generate or make a lot of design models. You configure the tools with different flag settings. You get the designs and fill the database. When you have your EDA tool trained, the tool may propose some tool flag setting in some new variant of a design, which may lead to better results. One of the critical things is that you get a sufficient number of design variants available, because randomizing over tool flags you can do with a classical constrained random generator. I think that's not a big deal to get it running. With the models of the design variants, it's a bit harder, and we have at Infineon something which you may call meta-model-based generation framework, whereas a meta-model, just in a short, is nothing else than a definition of a model. And we have 3 models involved, some high-level model, which is close to specification. We have one which covers a microarchitecture, but is more or less technology independent, and a few model which is close to the target language that you want to generate. And what's shown here is is quite common in the software area, and the OMG calls this framework, or the way how doing things, model-driven architecture. What we did is we applied it to hardware design. No. Okay. Now you want to say there's a lot of effort to build all the transformations and models and so on. But let's start with the right-hand side. The mapping of a design to a language, or a design model to a language model, is we do once and then you can use forever. So this part is no additional effort. The left-hand side, formalizing a specification, is something which we do at least since 10 years or more. It means having this flow available allows you to focus on one thing, to define a formal model of microarchitecture by considering specification items. So to say, you move the design generation from the language level to, so to say, the design level. So this ready-to-use unparsing and form stuff takes away from you the burden of formatting in your generator. You also don't have to take care about specific language features. The coding and language mapping is done automatically, and again, I already said you can focus on the behavior. Now, the point is, what does this do? What's this relationship of this to machine learning and to into EDA and data preparation? So this pipeline offers the opportunity, number one, to consider the translation. That means that you can generate design variants with few variants, and especially when it comes to different target architectures. And the greatest challenge is that you when one's having such a model, you can apply transformations to rebuild it. You can say to optimize it. For example, in a specification, you can filter out some parts which you simply do not want to have in specific design variants. Design model, let's say you can transform a design and do things like automated hardening or introducing security features or other things. And in the backend, you can go to different ways of describing things to make to utilize a tool in a better way. Now it means you have here in the pipeline a lot of configuration possibilities to get different models from one specification, and that's what we strive for, to have a lot of design variants. But that's not all. What you've seen before, you see here simplified as a gray box on top. And what's coming out additionally is that you apply this automatic generation for one component only, and for all instantiated components, you generate the instantiation and also the specification there. That means at the end, when you have a hierarchical design, you can configure any component in any level of hierarchy, and now I think you really can see that by having this possibility available, you really can generate a lot of design variants which give you the sufficient data to train your artificial intelligence. Now after having shown how training data, how so-called synthetic data generation can be done or is done, and how this the need or how the feature of configuration of transformation and translations helps here. Let's illustrate some more industrial use cases, what we did. One, I think you can learn more on this Friday, where a colleague of mine is talking about firmware driver optimization. I want to mention here that we used here the open source tool Verilator. Another optimization is something where we apply this is to optimize the hardware-software interface. In this case, we have a given number of bit fields, and we want to optimize the layout of a bit field under some application cases. And with case A and B simply illustrate two possibilities to place the bit fields in a register layout. What we are interested in is software size, hardware size, software performance, at least what we cover so far. You can think about more like power consumption, functional safety or robustness or other things. Now, how do we do it? To do the optimization, first we need a good estimation, and to do the estimation, my colleague Lorenzo made a mapping between picture processing, where you have several layers, and processing of bit field layouts, where you have different properties, like you write the bit field or read it, or have don't care bits or whatever. And after having randomized a lot of variants, in a lot of, we speak about thousands, maybe up to 10,000, and we can train the network. We have, I would say, a relatively small network in use here to do the estimation. The results, I would say, are quite promising, especially if you do a top-down design. You want to have some idea how to optimize the hardware software interface. I think we are always around 5% of the errors. Some of them, I would say, are easy to explain, but the register size should be easily derivable from a bit field. I think what surprised me was that we have that we can estimate the execution time of the firmware driver up to 6% in average, in the size of a binary code up to 2%. If you want to read more about it, the citation is shown below. Also important to say is that for doing this analysis, we use the Xilinx EDA-tool suite, the GCC, and again with the relator. The last application example I want to show is early physical design and floor planning. The point is that when starting a highly complex design, you have many decisions which impact the quality, and very early you have no idea about worrying about wire length and so on. So you really have to face a difficult decision-making process. And the consequence of that is that if you lay out today a medium to high complex chip, you start with quite a lot of uncertainties. You do a lot of trials, so to say. You can say you are in a search area, and this is time consuming and also quite costly. And only after a while in an execution, a lot of jobs, you have sufficient certainty that finally you reach the right setting, the right pre-placement, the right architecture to get the design as you want to do it. My colleague provided this slide, speaks in with certainty about red eyes jobs, because as soon as the machine is done, you immediately jump on the results, independent of the day or night time, see the results, do some changes, and restart the process again and again. So this also shows that help in this area is heavily needed. We do not see at the moment a quite solution there. What's now our vision, or what are we working towards? We have some chip dimensions, we have a die size, we have at least the first placement of the pads. We have a net list of a design, at least the first version. What we are striving for is a AI-trained tool. To use this tool, we use open source tools as well. And in just some seconds of runtime, we get a proposal for macro cell partitions, and then we even iteratively move around the macro cell placement and come up with new proposals which might be even better. When the pre-placement or the floor plan is ready, we extract constraints and then do a final placement with commercial tools, of course. And here you also see that now this AI-based tooling based on a lot of training runs really saves us time, makes our design time and also the design quality more predictable. It really creates value. Yeah, now let me close. Why do I think that we need more research in EDA? When we are already so many good ideas out, and that already some quite promising results have been shown. So what we observe at the moment, that the most delaying aspect in automating designs is the lack of design data, or of clean design data, which you can use to train the engines. So setting up the networks and training the networks, I would say, is the smallest part. It's really about getting the right design data right in time. It also means we observe at the moment also a delay in using AI for EDA tools, or at least an improvement which is gained by AI. What we need is human intelligence. We need research to come up with some human intelligence solutions to use machine intelligence. And also machine intelligence can a bit catch up, but my assumption or my proposal is that machine will never catch up human beings, but that's another story. So what I think what's needed, what are research directions to be followed? One is we need open source tools, or we need tools which allows us to do a lot of estimation is to collect a lot of data in order to train the tools, which mainly also means that we need more research contributions to open source EDA tools, and we are really happy that the tools like Very Late are out, but also that this huge project Open Road is there, and I hope that more people jump on there and drive this tool forward. We have to take care that the results which we get with the open source tools scale with the commercial EDA tools. That just to make clear, it does not mean compete with, but at least this tool should give us a hint what's the right way to go. We need a design data infrastructure. Most design flows are from different vendors, and even if you have a flow from one vendor, this design data are encapsulated in different databases. You have more or less access via different APIs. That's not the best starting point to do machine learning. So I think very important is also single way to access design data. Design data is not only physical design, it's also simulation, it's formal, it's property, specification, and many things more. And then we have a design data. We also need a learning-friendly structure to this design data, that we do not waste too much time to set up the training. Then, very important, even if this is more or less a research conference, we also have to think about the AI creates value, just 5% more, a bit more here and there isn't a big case. I have shown two applications where we really approach a new area of optimization. Between register layout is one thing, and I think the big stuff is floor planning. Whereas I know that we are not aware, but definitely we always should have in mind what business value can create AI, what business can be made with AI. Last but not least, it's really quite a huge effort to provide sufficient number of design data. So improvement in transfer learning, and I'm happy to see that also in this conference some approaches about transfer learning are shown, but here we must become more stronger. Last but not least, we need proving networks and models training data, and my vision is really that we foster the AI technology evolution in a way that we make it a factor of 1,000 smaller networks. Now you want to say, or you may say, 1,000 times, no chance. How can we achieve this? As a motivation, let me show this slide. And this slide is from the MIT paper cited below. And what the people were able to do is they found a new way of neural network. The network has only 75K parameters. And with this small network, they are able to drive a car, and the car is controlled by a camera, really. So when you take a look at normal machine learning or autonomous driving, what's done there, and here we speak more in terms of 100 millions of weights, and here we see a possibility to at least have some autonomous driving with a factor of 1,000 less weights. At least gives hope that we may sooner or later find similar brilliant idea also for application in machine learning for EDA. And I think with this motivation, I close my talk. Thanks for your attention, and I think now it's time for questions. Thank you.
Wolfgang, thanks a lot for your inspiring talk. And yes, as you were saying, it's time for questions. I believe, no, there's nothing in the Slack yet. Let me.
Hi, Wolfgang. I can ask a question if it's okay.
Go ahead, Ravi. Yeah.
Yeah. So first, many thanks for incredible and inspiring talk. You mentioned in early work that you did on coverage closure using random AI random test generator. Can you say a little bit, elaborate a little bit on what you did there and where did it struggle to generalize?
Okay, I can tell you why it struggled to generalize. The AI I didn't myself. If you are more interested, I can give you a pointer. Simply send me an email and I set the connection. So the point is that the randomization itself in UVM, which is the standard simulation approach for digital design at the moment, we simply were not able to hook in our randomizer to the commercial tool which we are using. And there was no hook, nothing, no API where we could feed the data.
Yeah. I can believe this very easily. Okay. Yeah, I'll be very interested to learn about the details there. It's very interesting. We are actually working on this topic, so it will be very interesting to read.
I have a question, Wolfgang, on the business aspect. I think that's very interesting that you touched on the business aspects as well. And one question I'm wondering about is, where do you think is the value in machine learning tools for EDA? Is it in the tool itself, or does the tool become valuable only after you have trained it? So is the training where the real value gets created? And if the latter is the case, if the real value is in training a tool for a particular application, then that raises to me the question how this can be handled by the EDA industry, because certainly if Infineon trains a tool to do a certain job, let's say physical design, for example, you would not want any other company to benefit from that. So could that point in the direction that more of the EDA tooling will be developed in-house again?
Oh, without any questions.
Yeah. So it's generally the question: where's the value? Is it the tool itself, or is it the training of an ML tool?
Okay, but no, but I think the value is in the reduction, in the effort reduction, or the quality increase which I get, or the performance increase which I get by a new or better tool. So this is where we have to start with. And only if there is value, then also people are able to pay more money or to spend more money in advancing machine learning for EDA. Now, interestingly, at the moment, we have quite a lot of research work also in big companies applying AI in design. As you said, one reason maybe that we have a training data, or that, so to say, the technology doesn't scale that easily. So the hope was that, for example, you can train a tool with one technology, and then, let's say, at the user side, you do a simple incremental training to adapt the pre-trained network to provide useful results. I would say no. It's not that we fear loss of know-how, because we have quite a good relationship to EDA companies. We also give them our designs to give them the chance to optimize according to our needs, or to fix the bugs and so on. So it's definitely, we are quite sure if we give a design to an EDA company that this is in a safe hand. So this is no, I don't see a problem. And really, if someone sees a problem, we can do something like a trusted data store that, for example, in Europe, this famous Gaia X, which you may have heard about, which is an open data space with accesses, which is really, this is doable. The point is really where do we create value with the tool? And for example, if you've seen, two of our examples are really areas where no EDA is there at the moment. So where we have some open space and we really can make benefits. And I also would say, if you see that we use with machine learning in EDA areas which are not covered by tools at the moment, at least what we presented also gives a hint. When you take EDA verbally, that means you automate your design. That means you write some algorithms, some computer programs that do some design steps now automatically, which you do before by hand. And the person who knows how to do this design is the users. So at the moment, I think we are in an area where the user use AI to code or to automate their design experience and to get forward. And that's, in my opinion, one reason why we see a lot of AI-based design automation at the user side.
Okay. Thanks.
I would have a question for me.
Sure.
Hi, Wolfgang. Thanks a lot for the talk. Very interesting. I have maybe a little bit nasty question and also a little bit more question on the landscape itself, because in your talk you also mentioned Google, and obviously, as you stated out, the business model of Google is completely different than the business model in the EDA community. But they also started, publishing papers on certain aspects of design automation. So, nasty question: do you see Google more as a partner, or activities by companies like Google more as some sort of partner within the community, or could something like Google or other big tech companies even become competitors, for example, to Infineon? A little bit nasty.
I think this is hard to answer. So what we see is that more and more system companies make their own chips. At the moment, I would not say it's a competition. It's simply that they make a chips where they have a knowledge to build the chip. They have a system understanding to build the chips. And we have some knowledge in other areas where we know how to build better chips. So yes, there is some movement that system houses make their own chips. We had, I think, the same thing 30, 40 years ago. Remember, the semiconductor had their origin in the system houses. I remember, for example, Bell Labs, TI. So I don't see this as a competition. Interestingly, what I observed, I think you for sure with Google paper, they were able to optimize the layout by a really amazing percentage compared to classical tools. So this is it's clear from my point of view that it's even possible to optimize with AI the state-of-the-art tools. If I read your paper correctly, when this was also a cooperation of Google with one of the EDA partners, so it's not Google alone. It's a good cooperation with EDA, and don't get me wrong. We only get good tools when we have a good cooperation there. So I'm happy and I'm optimistic that we will see outcome or results of this AI application or machine learning application EDA sooner or later in products.
Thank you.
So, more questions? Type into the chat or simply unmute yourself and speak up. While we're waiting, I have one more question, Wolfgang, which may be a bit detailed, but in your challenge 3 about the training data, you described how you use your generator to generate a large variety of results, which then machine learning can be trained on, if I understood it correctly. And what I'm wondering is, if you already have that generator design flow, well, you can use it to generate training data, that's correct, but the generator flow that already gives you the results that you're looking for. So where is the additional value in training a machine learning tool on that?
Okay, so number one, maybe I was not clear enough. The generator flow only gives me a design, and then I have to run an EDA tool to synthesize, to make the layout, to make the masks and so on. So it's the generator work more on the design side. Where is now why do I train the generator? What I can do is I can randomize a wide variety to provide a good data set, a good overview of all variants. And if you remember this picture, that we have many chances to make variations, and this on any component level and on any hierarchy level, the search space which we have is extremely huge. And you simply cannot try it out. And where we want to go with machine learning, number one, or first one is a fast estimation, and number two, of course, is to propose the right setting for a given application. Yeah, so but in this huge space of parameters, we get an advice in which direction to optimize the tool. And what you have seen from the cost functions, for example, which we have in other applications, of course, you are interested in the overall system throughput. Yeah, it's not the clock frequencies, the overall system throughput or the latency what I have. That means I have to consider a number of software code to be executed, the cycles needed to execute the code, the clock frequency enabled by the design. And at the moment, I think there is no closed theory or some idea how to make a cost model for these different contributors to your design features. And here really machine learning helps a lot, since it helps in a quite unstructured or at least undetected or unstructured, maybe better, area to find a way through optimization to come to good results, which you normally have no chance. Simply, how do we say in German? You don't see the tree in all the woods. So you have too many freedom, too many things to do to find the right path. And machine learning seems to give at least a feasible way for all the options.
Okay, thank you. Are there any further questions? I guess this is not the case at the moment. So then let me thank you again for your keynote, Wolfgang. Great to have you here. And then we move on to the next session on contributed papers. Helen Lee will be chairing that session. We are 10 minutes ahead of schedule. So Helen's probably best to take a 10-minute break and then stay on schedule, or what do you think?